Hey there. Welcome to AB Engineering Guild, your go-to reviewer for the Agricultural and Biosystems Engineering Licensure exam. In this video, we're going over the full solutions to the problems we've tackled in our previous videos from Part 1 to Part 10 under Area 1. So if you've been following along and want to check your answers or understand how to solve each problem step by step, you're in the right place. Ready to dive in? Let's break down the problems, one solution at a time. Solutions for Area 1. Part 1 to 10. 1. The cooperative plans to purchase 10 tractors to mechanize the farms and boost farmers' production. Each tractor costs 1.5 million pesos. The cooperative has 1.5 million pesos in its account, which will be used as a down payment to secure a loan from the bank. If the loan is approved, how much funding will the farmers receive to cover the remaining cost of the tractors? A. 15 million. B. 13.5 million. C. 10 million. D. 12 million. Okay, let us break down the problem first. It says that the cooperative wants to buy 10 tractors. Right. Then, the cost of one tractor equals 1,500,000 or 1.5 M pesos. Next. Total number of tractors equals 10 and the cooperative's available funds, for down payment, equals 1,500,000 pesos. They will use this amount as a down payment to secure a loan for the remaining amount. Question: how much loan, or funding, is needed to pay the remaining balance? The problem is this: the cooperative wants to buy 10 tractors. Each tractor costs 1,500,000 pesos, and since they need 10 units, the total cost amounts to 15 million pesos. However, the cooperative only has 1,500,000 pesos available, which they plan to use as a down payment. The question now is, how much loan or funding will be needed to cover the remaining balance? To solve the problem, we first calculate the total cost of the 10 tractors by multiplying the price of one tractor, which is 1,500,000 pesos, by the total number of tractors, which is 10. This gives a total cost of 15 million pesos. From this amount, we subtract the cooperative's available funds of 1,500,000 pesos, which will serve as the down payment. After subtraction, the remaining balance comes out to 13,500,000 pesos. This means the cooperative needs a loan of 13,500,000 pesos to cover the rest of the cost. Number 2. A 3-hectare field was plowed using a 15-centimeter wide animal-drawn plow at 4 km per hour and field efficiency of 75%. The draft required to pull the plow is 60 kilograms. Find the time required to plow the field. Choice A, 11.11 hours. Choice B, 22.22 hours. Choice C, 44.44 hours. Choice D, 66.66 hours. To find out how long it takes to plow a 3-hectare field using an animal-drawn plow, we start by understanding the given values. The total area of the field is 3 hectares, which is equal to 30,000 square meters. The width of the plow implement is 15 centimeters, or 0.15 meters. The speed of plowing is 4 kilometers per hour. However, not all movement is productive, only 75% of the time is actually spent plowing, due to turns, adjustments, and rest periods. This is called field efficiency, and it is equal to 0.75. The draft, which is the pulling force required, is 60 kilograms, but we won't need that for this calculation. Let's figure out how long it takes to plow a 3-hectare field using an animal-drawn plow. First, we calculate the effective field capacity, or EFC. This tells us how many hectares can be plowed per hour. The formula is EFC equals speed times width times field efficiency, divided by 10. Now let's plug in the values. The speed is 4 kilometers per hour. The width of the plow is 0.15 meters. The field efficiency is 0.75. Multiply 4 by 0.15, then multiply that result by 0.75. That gives 0.45. Now divide that by 10. The effective field capacity is 0.045 hectares per hour. That means, in 1 hour, the plow can cover 0.045 hectares of land. To find the total time needed, we divide the total area by the EFC. So, 3 hectares divided by 0.045 hectares per hour equals 66.67 hours. That's approximately 66 hours and 40 minutes. So if you're using this setup, expect to spend nearly 67 hours plowing the entire field. It's a long haul, but with steady pacing and good planning, it's absolutely doable. A plow with a 1 meter width travels 3 kilometers. What is the total area of the field plowed? Let's calculate how much land has been plowed by a farmer using a 1 meter wide plow. The farmer walks a total distance of 3 kilometers across the field, either in a straight line or through several rows. First, we convert the distance into meters. 3 kilometers is equal to 3,000 meters. Since the plow is 1 meter wide, every meter the farmer walks covers 1 square meter of land. To find the total area plowed, we simply multiply the width of the plow by the distance traveled. That's 1 meter times 3,000 meters, which equals 3,000 square meters. So, the farmer has successfully plowed a total of 3,000 square meters of land. A 4-hectare field was plowed using a 3-bottom 12-inch mounted plow. It took 11 hours to complete the operation at a tractor speed of 5 kilometers per hour. How many tractors are needed? We're looking at a real-world farming scenario. A farmer needs to plow a field that measures 4 hectares in total. To do this, he's using a mounted plow with 3 bottoms, and each bottom is 12 inches wide. That means the plow has 3 blades, each cutting a strip of soil 12 inches across. The entire task was completed in 11 hours using a tractor that moves at a speed of 5 kilometers per hour. Now, the big question is, how many tractors would be needed to plow the entire 4-hectare field within that 11-hour time frame? In other words, we want to know how many machines working together would be required to finish the job on time, given the equipment size and speed. Before we dive into the math, let's make sure we understand all the pieces: the total area, the plow size, the speed of the tractor, and the time limit. Once we've got those locked in, we'll be ready to calculate how many tractors are needed to get the job done efficiently. The given are as follows. The total area to be plowed is 4 hectares. The equipment used is a mounted plow with 3 bottoms. For those who may not be familiar, the number of bottoms refers to the individual plow blades attached to the frame. Each one cuts a separate furrow in the soil. Each bottom has a width of 12 inches, which is equal to 0.3048 meters. The tractor pulling the plow moves at a speed of 5 kilometers per hour. The entire task must be completed within 11 hours. However, not all movement is productive. Only 80% of the time is actually spent plowing due to turning, adjusting, and other interruptions. This is called field efficiency, and it is equal to 0.80. With these values, area, number of bottoms, width per bottom, speed, time, and field efficiency, we are now ready to determine how many tractors are needed to complete the job within the given time frame. Moving on, let's figure out how many tractors are needed to plow the field within the given time. First, we need to calculate how wide the plow is. The plow has 3 bottoms, and each bottom is 0.3048 meters wide. Multiply 3 by 0.3048, and we get a total plow width of approximately 0.914 meters. Now that we know the width, we calculate the theoretical field capacity, or TFC. This tells us the maximum area a tractor can plow in 1 hour, assuming there are no interruptions or losses. The formula is TFC equals speed times width times efficiency, divided by 10. But here's an important note, friends: when calculating theoretical capacity, we assume 100% efficiency. That means the efficiency value becomes 1, and sometimes it's not even included in the formula. So, we substitute the values: 5 kilometers per hour times 0.914 meters, divided by 10. That gives us a TFC of 0.4572 hectares per hour. In other words, under perfect conditions, one tractor can plow about 0.457 hectares in 1 hour. This sets the stage for figuring out how many tractors are needed to finish plowing the 4-hectare field within 11 hours. Now let's move forward. In the real world, plowing isn't perfectly efficient. There are turns, overlaps, and adjustments that slow things down. That's why we apply a field efficiency factor. In this case, the efficiency is 80%, or 0.80. To account for this, we calculate what's called the effective field capacity. This tells us how much land can actually be plowed per hour, considering real-world conditions. We use the same formula as before, speed times width times efficiency, divided by 10. Substituting the values, we get 5 km per hour times 0.9144 meters times 0.8, divided by 10. That gives us an effective field capacity of approximately 0.366 hectares per hour. This means that one tractor can realistically plow about 0.366 hectares in 1 hour. Now, to find out how much land one tractor can cover in the full 11-hour time frame, we multiply the effective field capacity by the time. That's 0.366 hectares per hour times 11 hours, which equals approximately 4.02 hectares. So, one tractor working steadily for 11 hours can plow just over 4 hectares of land. That's the key insight we need to determine how many tractors are required for the job. Finally, we compute the number of tractors needed. Based on our earlier calculations, if one tractor works continuously for 11 hours, it can cover approximately 4 hectares of land. And since the total area of the field is exactly 4 hectares, that means one tractor is enough to complete the job within the given time frame. No need for extra machines. It's just like cleaning a room. If one person can finish the whole thing before the deadline, there's no need to assign more people. You save time, fuel, and manpower. Efficient, practical, and cost-effective. So in this case, one tractor gets the job done. 5. A 4-stroke cycle diesel engine with 3 cylinders has an 89 mm cylinder bore and a 130 mm stroke. The compression ratio is 16:1, and it is running at 2,000 revolutions per minute. The question is, what is the total piston displacement? Let's break down the given. We're working with a 4-stroke cycle diesel engine that has 3 cylinders. Each cylinder has a bore, that's the inside diameter, of 89 mm, and a stroke length of 130 mm. The compression ratio is 16:1, and the crankshaft rotates at 2,000 revolutions per minute. Now, our job is simple. We want to find out how many cubic centimeters this engine displaces during every full stroke. Let's take a closer look at the data we've been given for this engine. First, the compression ratio is 16:1. This means the total volume inside the cylinder when the piston is at bottom dead center is 16 times larger than the clearance volume when the piston is at top dead center. This ratio is important for understanding engine power and efficiency, but it does not affect the geometric displacement. Next, we have the engine speed, which is 2,000 revolutions per minute. This tells us how fast the crankshaft is turning, and it affects how often the displacement volume is swept each minute. However, it does not change the size of the displacement itself. Finally, we're told that the engine operates on a 4-stroke cycle. This is relevant for timing and power delivery, but again, it does not influence the displacement calculation. So here's the key takeaway: when calculating engine displacement, we focus only on 3 things: the bore, which is the inside diameter of the cylinder, the stroke, which is the distance the piston travels, and the number of cylinders. Compression ratio, engine speed, and cycle type are important for other aspects of engine performance, but they do not change the physical volume displaced by the pistons. To find the engine's total piston displacement, we start by calculating the volume of one cylinder. The formula is pi divided by 4, multiplied by the bore squared, then multiplied by the stroke length. Substituting the values, we get pi divided by 4, times 8.9 centimeters squared, times 13 centimeters. That gives us approximately 808.7 cubic centimeters for one cylinder. Since the engine has 3 cylinders, we multiply that volume by 3. The result is about 2,426 cubic centimeters, or roughly 2.43 liters. Just imagine 3 identical glasses of juice. Each glass represents one cylinder, with the bore as the width and the stroke as the height. Multiply the volume of one glass by 3, and you get the total amount of juice, or in this case, the total engine displacement. Number 6. An agricultural machine is purchased for 100,000 pesos and has a useful life of 12 years. At the end of 12 years, the salvage value is 13,000 pesos. Using straight-line depreciation, what is the accumulated depreciation at the end of 8 years? Let's solve this step by step. An agricultural machine was purchased for 100,000 pesos. It has a useful life of 12 years, and its salvage value at the end of that period is 13,000 pesos. Using straight-line depreciation, we first calculate the total value the machine will lose over its lifetime. That's 100,000 pesos minus 13,000 pesos, which equals 87,000 pesos. To find the annual depreciation, we divide 87,000 pesos by 12 years. That gives us 7,250 pesos per year. Now, to find the accumulated depreciation after 8 years, we multiply 7,250 pesos by 8. The result is 58,000 pesos. So, by the end of the 8th year, the machine has depreciated by 58,000 pesos. That's your final answer, option C. 7. A farmer wishes to accumulate a total of P50,000 in a savings account after 5 years. The bank has a standard interest rate of 5% compounded quarterly. How much should he initially deposit? Let's summarize the situation. A farmer wants to accumulate 50,000 pesos in the bank after 5 years. The bank offers an annual interest rate of 5%, compounded quarterly. The question is, how much should he deposit today to reach that goal? This is a classic present value problem using compound interest. Now, let's go through the given values. The future value, or the target amount, is 50,000 pesos. The annual interest rate is 5%, written as 0.05 in decimal form. The compounding frequency is quarterly, which means interest is applied 4 times per year. The time period is 5 years. The unknown is the present value, or the amount the farmer needs to deposit today. If there were no interest at all, the farmer would need to deposit the full 50,000 pesos upfront. If the interest were not compounded quarterly, say, compounded annually, the growth would be slower, and he'd need to deposit more. If the time were shorter than 5 years, again, he'd need to deposit more to reach the same goal. So, each parameter plays a role in reducing the amount he needs to deposit today. Now, let's solve it using the compound interest formula for present value. The formula is, present value equals future value divided by open parenthesis 1 plus interest rate divided by compounding frequency close parenthesis raised to the power of compounding frequency times time. Substituting the values, we get 50,000 divided by open parenthesis 1 plus 0.05 divided by 4 close parenthesis raised to the power of 4 times 5. That simplifies to 50,000 divided by 1.0125 raised to the power of 20. The result is approximately 1.282037. Finally, 50,000 divided by 1.282037 equals approximately 38,984 pesos and 48 centavos. So, the farmer needs to deposit about 38,984 pesos and 48 centavos today. If he leaves that amount untouched, the power of compound interest will grow it to 50,000 pesos in 5 years. No additional deposits needed, just time and interest working together. 8. A field measuring 45 m by 90 m is to be prepared using a 1 meter wide upland power tiller moving at 3 km per hour, with a 10% overlap and 9 seconds turnaround per pass. What is the actual field capacity when tilling is done along the longer side? Let's summarize the situation. A farmer is preparing a rectangular field that measures 45 meters by 90 meters. He's using a power tiller with a blade that is 1 meter wide, operating along the longer side of the field. However, due to overlap between passes, only 90% of the blade's width is effectively used. That means the actual working width is 0.9 meters. The tiller moves at a speed of 3 km per hour, and after each pass, the operator takes 9 seconds to turn the machine around. These factors, effective width, speed, and turnaround time, all affect the actual field capacity, or AFC. Now let's solve this step by step. First, we adjust the implement width. Although the blade is 1 meter wide, there's a 10% overlap. So we multiply 1 meter by open parenthesis 1 minus 0.1 close parenthesis, which gives us 0.9 meters. If there were no overlap, the full 1 meter would be used, but that could leave gaps in the soil. Next, we convert the speed into meters per second. 3 kilometers per hour is equal to 3,000 meters per hour. Divide that by 3,600 seconds, and we get approximately 0.833 meters per second. If we didn't convert the units, our time and distance calculations wouldn't match. Now, we calculate the time it takes to complete one pass. The field is 90 meters long, so we divide 90 by 0.833. That gives us about 108 seconds per pass. Then we add the turnaround time of 9 seconds, bringing the total time per pass to 117 seconds. Without accounting for turning, we'd overestimate the machine's efficiency. Next, we find the area covered in one pass. Multiply 90 meters by the effective width of 0.9 meters, and we get 81 square meters per pass. If there were no overlap, this would be 90 square meters, but again, that would risk missing parts of the field. Finally, we compute the actual field capacity. We take the area per pass, which is 81 square meters, divide it by the time per pass, which is 117 seconds, and then convert the result into hectares per hour. The final answer is 0.25 hectares per hour. That's the true working rate of the tiller under these conditions. So to confirm, although the initial estimate in my first video was 0.75 hectares per hour, the correct calculated answer is 0.25 hectares per hour. 9. Determine the number of 13 centimeters animal-drawn plows needed to complete plowing a 3-hectare field in 1 day, 8 hours, given a field efficiency of 78% and speed of 3 kilometers per hour. Let's summarize the situation. A farmer needs to plow a 3-hectare field within 1 working day, or 8 hours. He's using animal-drawn plows, each with a blade width of 13 centimeters, which is equal to 0.13 meters. The animals walk at a speed of 3 kilometers per hour. Because field work is never perfectly efficient, we apply a field efficiency of 78%, or 0.78. These values, width, speed, efficiency, time, and area, will help us determine how many plows are needed to finish the job on time. Now let's solve this step by step. First, we calculate the effective field capacity of one plow. This tells us how much land one plow can cover per hour, factoring in real-world losses like overlaps, turns, and rest periods. The formula is, effective field capacity equals speed multiplied by width multiplied by field efficiency, divided by 10. Substituting the values, we get 3 kilometers per hour times 0.13 meters times 0.78, divided by 10. That gives us approximately 0.03042 hectares per hour. If we didn't account for field efficiency, we'd overestimate the plow's productivity. Next, we calculate how many plows are needed. The formula is, number of implements equals total area divided by open parenthesis time multiplied by effective field capacity close parenthesis. Substituting the values, we get 3 hectares divided by open parenthesis 8 hours times 0.03042 hectares per hour close parenthesis. That gives us approximately 12.33 plows. Since we can't use a fraction of a plow, we round up to 13. So, the farmer would need 13 animal-drawn plows working simultaneously to complete the field within 8 hours. If the speed were faster, or the plow wider, fewer implements would be needed. If the field efficiency were lower, or the time available shorter, more plows would be required. Final answer. To confirm, although the initial estimate in my first video was 5 plows, the correct calculated answer is 13. 10. Given a 2-row corn planter with 75 cm row spacing and a ground wheel diameter of 60 cm, what is the expected hill spacing using a seed plate with 20 cells and a gear train ratio of T1 equals 6, T2 equals 18, T3 equals 10, T4 equals 25? Let's summarize the situation, guys. We're working with a corn planter, and our goal is to determine the hill spacing. That's the distance between seed hills along the same row. To do this, we need to understand how the planter's components work together. The ground wheel drives the seed metering mechanism, the seed plate rotates to drop seeds, and the gear train controls how often the seed plate turns. Each cell on the seed plate holds one seed, and gear teeth transmit motion between gears. These parts all influence how far the planter travels before dropping the next seed. Now let's go through the solution step by step. First, we calculate the circumference of the ground wheel. This tells us how far the planter moves in one full wheel revolution. If we didn't know this, we couldn't measure the planting distance accurately. Next, we determine the gear train ratio. This is the product of the ratios between connected gears. It tells us how many times the seed plate rotates for every one turn of the ground wheel. Without this ratio, we wouldn't know how often seeds are dropped. In this case, the seed plate rotates 2/15 times per wheel revolution. Since the seed plate has 20 cells, it drops 20 seeds per full rotation. But because it only rotates 2/15 times per wheel turn, it drops approximately 2.67 seeds per revolution of the ground wheel. Now we calculate the hill spacing. The ground wheel travels 188.5 centimeters per turn, and drops about 2.67 seeds in that distance. Divide the distance by the number of seeds, and we get approximately 70.68 centimeters between seed hills. Finally, we convert centimeters to meters. 70.68 centimeters is equal to 0.71 meters. So the hill spacing is about 0.71 meters. If the gear ratio were higher, the seed plate would rotate more often, dropping seeds closer together. If the ground wheel were larger, the spacing would increase. Every component plays a role in achieving precise planting. And that's a wrap, guys. We've just completed the full set of solutions from parts 1 to 10 under Area 1 of the Abele review for the year 2025. Each problem was broken down step by step, with clear explanations and practical insights to help you understand the logic behind every answer. Whether we were calculating field capacity, engine displacement, depreciation, or hill spacing, we made sure to define each parameter, explain its role, and show what happens if it's missing or misunderstood. From plow width and speed, to gear ratios and compound interest, every value had a purpose, and every formula told a story. If you found this helpful, don't forget to like, subscribe, and hit the bell icon so you stay updated for our next videos. If you have questions, suggestions, or topic requests, feel free to message us on Facebook or send an email to abengineeringworld@gmail.com. We'd love to hear from you. Study well, stay focused, and as always, Kaya Mo Yen. Don't forget to pray, Mga Baya, because without it, the journey gets harder. See you in the next one, and good luck, future engineer.